Hello and welcome, and a little bit more emphasis on welcome than usual today, I think, because I have a feeling that there's going to be an above average number of new visitors to my channel and people going, what the heck is this? I'm just back home from the Microsoft Excel World Championships finals in Las Vegas, and I won. Woo! So today I'm going to be doing a walkthrough of the case from the final, which is called Origami by Klinsmann Langhans. But first, let me give a bit of a, what the heck is going on here? What is an Excel competition? I will say that there's a financial modeling competition that is, do build forecast models and do the kind of things that you might do at work in finance. That exists, but that's not this. This competition is like no domain knowledge. It's just problem solving in Excel. Um, so what does that look like? It looks basically like a coding competition. And if you're used to using Excel mostly for, like writing to-do lists or summing up a handful of numbers, it might seem weird to you that something resembling a coding competition could happen in Excel, but, well, watch on and you'll see what we do with it. It gets kind of wild. So I'll explain this particular case in a minute, but just general layout, what do you get? You get some instructions, and then you get usually 7 different levels. And so for each level, you have some question you need to answer, and there's an example given. So, if the input was this, then the output should be 6. And then you have a bunch of other inputs that you have to work out the answer for. Usually 10 or 20 questions, 10 or 20 sets of inputs per level. And the levels build up in difficulty and usually build on top of each other so that, what you've done in the earlier levels makes a difference in the later levels. And then there's also kind of 5 independent bonus questions. That are just a single question each. So again, I'll talk more about this particular question later, but the idea is within usually half an hour. For the finals case, it was 40 minutes, just because it's a little longer and a little harder. How many points can you score? So every question here has a point value. Every bonus question has a point value, and generally, the later levels have the higher point value. So all the levels together add up to 1,000. The bonus points add up to 250, and it's just who can get the best score within the time. Now, let's talk about the finals case. And an important piece of context I have to give you here is obviously the finals of the World Championship. You would expect the challenge to be hard. One of the ways that has been achieved in the past is by having a very high degree of complexity. So for last year's final, there was a case based on World of Warcraft, where you had to follow through quests, track your experience, track your gold, track your skills, and so on. But before we went on the stage for that, they gave us this, I am not kidding, 7-page instruction manual with details of what happens in each level and how it works, that we had to, sit and read and digest and make notes on before we went on stage. Before we went on stage this year, we got one double-sided piece of paper. It had approximately 1 paragraph of text, and it was almost entirely explained by the name of the case, Origami, and then the visual instructions on the second page. So the idea is we have a sheet of paper, meaning an Excel grid, and this is, an example of what the giant sheet that we're given in the actual case looks like, and we have to fold it. So, if you fold up, then the bottom part gets flipped and goes to the top, and the original top part gets covered up. So you just get this. So this bottom line is now the top line, and then the second line is now the second highest line, and this is all zeroed out. And similarly for the diagonal, the main diagonal stays in place, and then everything else flips around it. So this bottom line from 57 to 64 is now running here from 57 to 64, and same for a flip to the right. And then you get into multiple folding. So, first you fold it up and to the right, then you fold it down, then you fold it to the right. The one thing to watch out for here, it only really comes up in the last level, because you can't get to it if you're just doing left and right and up and down folds, and the diagonal doesn't come in until later. But if you look at this one here carefully, like with this fold to the right, you just take the left-hand side of the grid, flip it over, and just delete the right-hand side. But here, you can't delete the right-hand side because there isn't any paper here, which means that this bit doesn't get covered up. So that's just one nuance to be aware of. So you've got, like, this bit is the paper that was folded over, and this bit is the paper that was underneath but is still visible. But that's basically it. Like, that picture tells you everything you need to know about the case at a high level, and then obviously you get into details on what specific questions are being asked. The last thing to explain by way of context is, in the final, there are a few extra format twists, which is A, it's 40 minutes because the case is really hard, but B, there's a staged elimination. So 12 people make it to the final stage, and every 5 minutes, whoever's in last place gets eliminated so 6 people get eliminated over 30 minutes, and then the last 6 people get to play out the last 10 minutes. And the second thing is that these bonus questions are only available for 6 people. So there's usually a bit of a scramble to get the first few bonuses. All right, I think that's enough general background. The one other thing I will say is I tried recording a video of this where I both solve the case and try to explain it in a way that's friendly to new people, and that video ended up being unreasonably long. So I'm gonna have to speed it up a little bit, but I haven't figured out exactly how to do that. But let's just see how it goes. So here is our giant sheet of paper. It's very, very giant. And I'm just going to go ahead and give that a name to make it easier to refer to. So I'm going to call that paper. And you can just check here. It's 256 columns and it's 256 rows. So we've got one giant square. So let's get into it. What is the sum of the main diagonal, top left to bottom right? Now, there are easier ways to do this, but the way I did it was sum of paper times m unit 256. So m unit gives like a unit matrix. Or it's like the identity for matrix multiplication. So if you say m unit of 4, for example, it gives you a matrix that is, sorry, let me zoom in, gives you a matrix that is 1 along the diagonal and 0 everywhere else, and is 4 by 4. So that's a quick way to pick out the main diagonal. What is the sum of the 4 central cells located in the very middle of the sheet of paper? So for this, we can say, so it's 256 by 256, which means that the 2 in the middle will be row 128 and 129 and column 128 and 129. So you can say index paper by 128, 129, and so that's the row numbers, and then the column numbers 128, 129. And that gives you the middle blob of the grid. The thing to be careful with is there's a slight subtlety that this is a semicolon, not a comma. If I give it a comma, then it's saying, well, here's 128, 128, and here's 129, 129. But if I do a semicolon, which basically means these are stacked vertically on top of each other, these are side by side, then it will broadcast and give you all 4 intersections. So just got to be a little, whoops, not substitute, but sum, got to be a little careful there. Okay, so that is bonus 2. Bonus 3, what is the largest sum of numbers found in any 5 by 1 vector in the sheet of paper, vertically or horizontally, no diagonals? Now this is a good place to introduce another very, very important piece of the meta, so to speak, of competitive Excel, which is the concept of custom functions. So Excel allows you to write, using the lambda function, custom functions that do all kinds of things. So in this case, I've got a custom function because this kind of question comes up semi-often, like, you know, what is the biggest sum in a 5 by 1 or the biggest sum in a 3 by 3, or, you know, how many 2 by 4s contain x or whatever. So I've got a function I've written called birectangle. Sorry, first I have to import my functions, for which I'm going to use this little add-in called OA robot. I just call, what? Okay, try again. That's better. So just call that and it pulls in all of my custom functions. I've got a whole bunch of things here. You can see that most of them start with lambda, which means those are functions. A few of them are just stored values. Okay, so then if I say, well, let me just show you a mini example here. If I say by a rectangle of, let's say, this little 4 by 4, and I want the sum of each 2 by 2, then it will tell me the sum of this 2 by 2 is 59, and the sum of this 2 by 2 is 40, and so on all the way down to this 2 by 2, which is 53. So what I'm going to do is apply that to the whole thing, and then take the max of that. So I'm going to take max of birectangle. The range is that whole paper sheet. The function is sum, and it's 1 by 5. So that will give me one way around, and then I also want the other way around, which is 5 by 1. So I'll just do that again and take the max of both of those, and that is 98. Okay, next up, always folding from left to right and considering that each fold reduces the size of visible cells by half. What's the sum of the visible cells when the sheet of paper reaches a width of 4 columns? So a couple things here. 256 is 2 to the power of 8, I want to say. Yes, and 4 is 2 to the power of 4, so basically we want to fold it in half 6 times to get from 256 down to 4. So if you want to apply a function a certain number of times, a good way is to use the reduce function. So we'll say reduce we're going to take 6 steps. We won't actually use the variable, but this will give us an array of 6, so it'll iterate through it 6 times, and then we need to write a custom function for what we want to do at each step. And we're going to say, I guess I'll call it lambda of grid and just an underscore because the second argument is not used. That's just the counter. So what do we want to do? First, we want to take the left-hand half of the grid. So we'll take grid columns of grid over 2. And then we want to sort that. So we want to take the left-hand side, put it onto the right-hand side, but then we also want to, so that it's flipped around, we want to sort it. So to do that, I'll say sort by, and I'm going to sort it by sequence, comma, so that I'm giving it a column argument so that the sequence is going across. And then I want columns of grid over 2, and sort in descending order. So this will give me a sequence that goes 1, 2, 3, 4, 5, 6, 7, 8 up to, in the first case 128, in the second case 64, and so on. And I'm going to sort by that in descending order so that it'll flip everything around. And if I have that right, then if I step that 6 times, that'll get me folded until we're down to 4, and then I sum that up, and we're good. Hooray. Okay, and then what is the center cell of the only 3x3 square that contains all the numbers 1 to 9 on the sheet of paper? So here again, I'm going to birectangle. I'm going to operate on the sheet of paper, and it's going to be 3x3, and now I need a custom function. And what I want is a function that will say, if this 3x3 has all the numbers 1 to 9, then give me the address. So first we'll say, so the function will take an argument, which is the input, and do something with it. So I'm going to say the square is the function. So first I want to flatten the square, so I'll say toCol of square, and then I want to sort it. And what I want to test is when I've flattened it and sorted it, it should then be 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm going to say sort is equal to sequence 9. That will give me 9 different true or false values, and if all of those are true, that means we've got the 9 numbers we want. So I'm going to wrap that in AND to say they all have to be true. If that's all true, then I want the address of the middle cell. So I'm going to use my custom function, which is addresses. Just give it a range and it returns the addresses. I'm going to say the addresses of square, and then I want the middle one of that. So we'll say index of that 2, 2. And if it's not the numbers 1 to 9, then I just want double quotes. And so that will give me a giant grid that is almost all blank strings and then one cell value, and then I just want to concatenate that together. So we'll concat that. And that is the bonuses. So now we get on to the main questions. And here I'll just sort of introduce you to some of the levels, introduce things bit by bit. So first, we're just looking at referencing with this slightly odd format. So, R2, C2, we're interested in the thing in the second column and the second row here. And then we've got a bunch of other inputs to say, what's in these cells. So that's one thing that we need to work with. Then the next thing is we have to actually, so here we're just working with this mini grid here, but for the rest of the time we're going to be working with subsections of this giant sheet of paper. So here, for example, we're centered on HY123, which is this cell containing the 1, but it's size of 7, so we go kind of 3 to the left and 3 to the right, and 3 up and 3 down to make a square. And then later on we'll have a top left cell and an 8x8 square, or a top left cell and a variable size square. So those are two things we need to handle before we can even get into folding. So let's do it. I'm just going to take this grid, I'm going to mark as input because that's part of the lambda setup. Just shrink these columns. I'll call that array, and then I'll call this ref. I just take this. So this is, I'm just setting up for the robot tool that I showed you earlier. Has some handy functions for generating your own custom functions quickly and easily. So I'm setting up to use that. So just narrow out a bunch of these columns. Sorry, wrong one. So first I want to extract the numbers from this reference. So I'll just call that coords. We'll say regex extract from here. /d matches any digit, and a plus will match multi-digit numbers, and I want to return all matches. And that gives me 2, 2. But then if if we're working with a bigger grid later and there's a 24, that 24 will come out as that. Whereas if I just said match any digit, then the 2 would come out as one match, the 4 would be another match, and the 2 would be another match. So that's my coordinates, and then my output is going to be index on this grid by this row and this column. Now you could write this all as one thing, so you could say let array be this, and let ref be this, and let chords be regex extract of ref slash d plus 1, and then you could say index array. But then, because coordinates is part of this kind of extended calculation, you can't just click on the left-hand side of it, click on the right-hand side of it. So you'd have to say something like, index chords 1 to get the first coordinate, and then index chords 2 to get the second coordinate, and that would do the same thing. But part of the fun of the robot setup is that it will make that easier for you. So I'm going to call the command generate lambda statement now, and it will make me a new custom function that takes 2 inputs, an array and a reference, does these interim calculations just like I did, and here you'll see that it's automatically made these dynamic array friendly references. So it's taking the first column of coordinates and an @ just to make sure you get a single value. If you don't understand that, don't worry about the technical details, and taking the last column and applying that. So now I'm going to save that lambda, and I'm going to call it ref from grid. And so now level 1 is nice and simple. It's just ref from grid of this grid, lock, and this reference. And because we've locked the reference to the moves, we can just copy that down. So for level 2, then we need to find areas from the paper. Now you can do that with some mix of offset and indirect. So if I said indirect, let me just grab this, and then come back. Oops, what are we doing? Okay. So indirect basically lets you give a text string. So I'm going to put the sheet name in single quotes with an exclamation mark, which is how Excel makes references, and add to that the cell that we're interested in. And then the indirect of that string will give me a reference to that cell, and then I can say I want to go 3 back, 3 up, and to a height and a width of 7 and 7, and that will give me this set of numbers. But offset and indirect are desperately slow, so I do it a different way with my own lambdas. So basically, I convert everything to a row column reference, which is 1,000,000 times the row number plus the column number. So here, this is row 123, so it's 123 million, and HY is column 233. So this is 120,233. And then if I want to say, okay, go 3 steps diagonally up and to the left from that, well, going up is just minus 1,000,000. Probably don't have the right number of zeros there, but anyway, I have a stored variable because I use this row column reference a lot. I just m is 1,000,000. So going up a step is minus 1,000,000, and going left a column is minus 1. So we're going to subtract 1,000,001 3 times to get up to the row column reference for that top corner. So we'll say minus, we'll say this minus 1 over 2 times m plus 1. And that gives me the reference for the top left, and I can also convert that back to an address. And that tells me it's HV120. And I can do the same thing for the address of the opposite corner and combine those together. And this with a colon, 2 cell addresses with a colon in between, is how Excel thinks of ranges. So if I put that in here, it takes me to HV120 to IB126. And then we want to do stuff with that. In this case, we just want to sum it up. So then I can say 2ref is my more efficient version of indirect. 2ref of that on paper gives me what is in this cell range address in the range paper. Now, this idea of pulling out a subset of the grid is something we're going to have to do a few times. So let's, again, sort of robotify that. I'm going to change it a little bit. So I'm going to say cell. And rather than just using the 7, because then we'll have to do things differently when it's the top left corner as opposed to the middle cell, I'm going to do a top left offset, and I'm going to do a bottom right offset. And in this case, the top left offset is -3, the bottom right offset is 3. I'm going to mark all 3 of those as inputs, and then just replace the relevant bits here. So to RCRef that, we'll replace all of this number with plus that, to RCRef of that, and again replace all of this with that. And then call that out, and let's generate lambda state. Actually, we can just go straight to save lambda. And I'm going to call this one, oh yeah, this, well, it doesn't matter. I'm going to call this one, try again, save lambda. I'm going to call this one from paper, because it lets me get a grid from the paper. And in this case, I'm just interested in what is the sum of the numbers within a square. So we're going to say sum of from paper, this cell, and the row offset is going to be this -1/2 for the top corner, and then the same thing but with a positive sign for the bottom corner. We sum that up, that's 439, all good. So now we have to do the folds, and then we're basically good to go. So the way I think of the folds is kind of mixing two things. So one is a transformation. So in this case, if you think of just flipping the whole piece of paper so that it sorts left to right, right to left instead of left to right. And then the second thing is like a mask to zero out one part of it. So we're not interested in having anything on this side anymore. We just want this side. So in this case, we're doing folds from left to right, and it's always 8 by 8. But let's be ready for something more general. So we want, first let's get from paper. This is our cell. Top left offset is 0, and the bottom right offset is 7 to get an 8 by 8. So we end up with this, just like here, 9, 4, 15, 15, down to 14, 7, 3, 19. Yep, so that's all working. So then, to flip it, I've already got a custom function called flip that can, by default, it'll flip both vertically and horizontally. So this 9, 4, 15, 15 ends up being down here, reading from left to right now. So, you know, it's flipped top to bottom and left to right. But in this case, I'm only interested in flipping left to right. So I just put in the optional argument for not vertical. And then I get, yeah, so over here, 15, 15, 4, 9, 15, 15, 4, 9, and down at the bottom, 1, 4, 8, 11, 1, 4, 8, 11. That's good. So that's my transformation. And actually, let's just set this up for robotification. So we'll say my array is that, and we'll mark as input. Then my transform is that, and then I need my mask, which is, so I want to zero out the first 4 columns. So I'm going to say sequence, comma 8, give me that, and actually let's just make it dynamic right from the start. So we'll say sequence columns of the array, give me that, and if I'm only interested in the right-hand side, then I need that to be greater than columns of the array over 2. And let's just, that gives me trues and falses, but if I minus minus, that'll convert them into numbers. So we get here, these 4 columns are true, these 4 columns are false. And so then what I want is if mask, then transformation, otherwise 0. And that gives me that. But now the nuance I mentioned with the multiple folding, where you might need to see what's underneath, that we're not dealing with that right now. So let's fix that. So instead of saying give me the transformation, I can say if the transformation is not 0, is greater than 0, then give me the transformation. Otherwise, give me back the original array. And that is basically going to be the template for all the, like, it's going to be different transformations, flipping other ways, and it's going to be different masks for which columns to show, but that's going to be the template for all my flip functions. So I'm going to generate lambda statement. Why does it have 2 arrays as inputs? What's the second array here? I can't see what it's pointing at. Thought I only had 1 input here. Let's just copy value, paste that to be safe. Wait, I bet I know what it is. Because I saw that this was not an array reference. I bet it's because I've, no, it's not. I'm confused. Anyway, all right, I am going to undo that and copy value paste this. I don't think that's the issue, but let's just be safe. So we do that and this. And try again. Okay, now we're down to one input. We're still, why is it pointing to top left cell? G134. Shouldn't be anything pointing to that unless I've done it wrong. Ah, sorry. Okay, now I see the problem. This is pointing back to here when it should be pointing to, I pulled this out to use it separately, but then I should have used it. That's why it's getting mixed up. Didn't write that a very good way. Okay, so now we'll generate lambda statement. We have one input, we have a transform, a mask, and then a result. That's exactly what I want. I'm going to say OK. And then I'm going to save lambda, and that is going to be my flip right. Flip right. Okay. So now I can say from paper of this 0, 7 gives me the 8 by 8. Then flip right of that gives me this thing over here, and then I want whatever I called it, the grid ref something, ref from grid, yes. Of that with this reference gives me 20, and we're all good there. Okay, so now for the next level, we have to be able to do flips in the 4 orthogonal directions. So let's come over here. And it's a pretty simple edit at this point because to change this from a flip right to a flip left, I just have to make that less than or equal to. And now we're keeping this side because it's the same horizontal flip, just the mask is changing. So I'm going to save that lambda as, and we'll call that flip left. And then for, just move this over here, a little more space. For the vertical, it's just going to be a case of flipping the orientation of the mask for where we're hiding. So let's edit lambda again. And we'll change the orientation of our mask, and we'll change the direction in which we flip. So I don't want to flip horizontally. Now I want to flip vertically. So I'm going to say not horizontal, but keep vertical. And so now we have, where's our original? Here. So I have 11.841 going up to the top, 11.841. That looks good. So I'm going to save lambda as again. That's my flip up. And then edit lambda. And I'm going to change that less than or equal to a greater than. And now I just have the bottom 4, and I'll save lambda as. And that's my flip down. And while I'm at it, I think I'm just going to do all the rest. So the transform. I'm just going to make my mask be 1 for a second so that we can see the whole transformed grid. So the transform that I'm interested in for my diagonal flips, the first one is going to be just transpose. And we don't need a second argument there. So now my 11.177, sorry, this is my original, my 9.4.15.15.7 becomes down here 9.4.15.15.7. So now my mask, what's that going to be? Well, it's going to be, sorry, keep the minus minus. So I think if I do, so I have one sequence running down, and if I have another sequence running across, so move that to the column argument, that will give me, yeah, that's my, I need a greater than or equal to include the main diagonal, but that's my bottom left half. So then we can take this, yeah, let's just take this. And replace this with array and this with array. Oops. Then we'll save lambda as, and that is my flip down left. And then if I edit lambda, and again just change this from a greater than or equal to a less than or equal to, now we keep the top half, and that's my flip up right. So save lambda as again, flip up right. And then we edit again. So now for, yeah, I think for this, what I want is one of these counting down. So let me just show you that for a second. So what I want is, extra comma there. So I want is this counting from 8 down to 1, and then I want to compare the other one to that. Yeah, so that's going to give me my bottom right corner, and then the same thing like that will give me my top left corner. So let's change the mask to that. So we'll say columns of array, starting at columns of array and steps of -1. So now I'm keeping my top left corner, and the transformation to do the flip, from this corner to this corner, from here to here, is going to be left to right flip, a top to bottom flip, and a transpose. That, I'll be honest, took me a minute of just sitting noodling on the stage, but you can always grab a piece of paper if you're unsure and try it yourself. But this takes this 19 up to the top left corner, that's good, and then let's just see, this 4, 10, 7 should now be, well, the 7 is currently hidden because of the mask, but yes, it's 4, 10, 7 in the other direction. Okay, that's good. So that's my flip up left. So I'm going to save lambda as flip up left, and then one last edit. And I will change this to be greater than or equal to, so that I get the other side, and that's flip down right. Okay. Whew. A lot of work there, but now that we've done all of that, it's going to make the last few levels fall out quite quickly. Right, so the last thing I want is I need to be able to make my my direction a variable. So I'm going to write one more function that calls each one of these functions. So I'm going to say lambda of an array and a direction. I'm going to choose, I'm going to x match the direction against my list of arrows, which is just what I've outputted into the grid here. And then we're going to choose based on that. So this will give me a number between 1 and 8. If it's 1, it's going to be this. If it's 2, it's this. 3 is that. 4 is that, and so on. And I just want to give it a corresponding function. So first we're going to say flip left of array, and then let's do, that's not a very good way to do it. Whatever, it doesn't matter. So that's 2, 3, 4, 5, 6, 7, 8, and close and close. So then it's going to be flip left, and then flip right, and then flip up, and then flip down, and then flip up left, then flip up right, and then flip down left, and then flip down right. I should say I've spent like a bunch of time developing kind of all in one go here, which wouldn't be a winning strategy in the competition because I would have been eliminated by now for not having enough points on the board. But I think it's easier to understand if you see all the functions coming together at once and then use them. But I don't know. Tell me if you disagree. Okay, so finally we can get something done here. So I want to get a from paper. This is my top left cell, so no top left offset, and the bottom right offset is going to be that -1. That's going to give me a 6x6 grid. Then I want to apply a flip. So we'll flip all of that based on this direction, and then I want to get a reference from that. So it'll be ref from grid of that and this reference. And this is where the function setup really, really pays dividends, because you can write super simple functions that solve quite complex levels. So now, double folding. Again, not nothing too complex with the setup we have, so we'll go from paper. This 0, this -1. That gives us the grid. Then if we want to do something multiple times, we can reduce. I'm going to reduce through a sequence which is the letters of this. And at each stage, I want to flip all. And so this will call flip all on the original grid and the first letter from this, which is the right arrow. Then it'll call flip all on the grid that comes out of that and the second one from this, which is the down arrow. So that gives me that. And then I want to ref from grid of that and this reference. And that gives me 4. Okay, now diagonal folding, we're basically, actually this quadrant is an extra complication, so I'm going to do the same as I did in the actual competition, which is solve level 7 first, because that we're basically already set up for. So I want from paper of this top cell 0 and that -1. That's going to give me the 6 by 6 grid, and then I want to reduce that through the letters of this. Actually, can I just, yeah, I think I can just copy my exact function from here. Oh no, that ends up with a ref from grid, so that won't quite work. But then if I replace ref from grid with just summing them all and get rid of that, yeah, that works. So yeah, once you have the kind of flexi setup, level 7 actually easier than level 6. But now for level 6, what do we need? We need to identify a quadrant at the end. So how are we going to do that? Well, let's start with a sequence of 6. I'm going to set up a pair of masks here. So sequence of 6 greater than 6 over 2. That's going to give me, let's again transform that from trues and falses into zeros and ones. So that'll give me 0 or 1. And then I want to do the same thing here. So take the whole formula, put it here, and then just have this going across instead. And so using this, I can number the grids. So I'm going to say 1 plus this plus 2 times, sorry, no, do it the other way around. It'll be more natural reading order. 1 plus that plus 2 times that. So that's going to number my top left quadrant will be 1, next quadrant will be 2, 3, and 4. And that I think is a pretty decent setup for that. So let's just take these in here, including the brackets. So put that over this one, and we'll take this one, and put it over this one. Okay, so now I just need to identify these with quadrants. So we'll do sort of unique of these arrows. So this is going to be quadrant 2, this is going to be quadrant 4, this is going to be quadrant 3, and this is going to be quadrant 1. And then let's just sort these in that order. So then, what are we trying to say? We're trying to say from paper of this cell 0 and this -1. We want to apply a transformation to that, which will be flip all of that and this. And then we want to multiply that by this mask, which is going to be this times, I'm going to just grab this. Not ideal to write all this in one formula, but I'm just going to do it anyway. So that's my mask, and then I want that to be equal to X match of this arrow against this list of arrows. And actually, we can just hard code that. So that zeroes everything out except for 2010, 2011, 7, 2010, 2011, 7, 19. Yep, good. And then we just wrap that in a sum and bring it in here. And that checks out. And I think that's everything. Oops, I've shrunk my columns too much to be able to see the score. Yes, all right, that's 1250, which is full marks. And on a second go, at least, I solved it almost as fast as I did on the night while doing at least some explanation. So I'll take that. I guess the other thing, again, since there's lots of new people here, if you are both new to this and nevertheless made it to the end of this video, then you sound like an Excel enthusiast and you should come join us because there is an amazing and warm and welcoming and fun community around this whole game. So yeah, sign up, give it a go, or get in touch with me or with others who do it. There's a whole a super active WhatsApp group where people exchange thoughts on approaches, root each other on, help each other work out issues with their custom functions and all kinds of things. It's a great place to be. So yeah, come join us. That's all I got for today. Thanks for watching. See you next time.